Hi everyone. Imagine your microcontroller is constantly screaming, is the button pressed? Is the data ready? Is the timer done? 100% CPU usage. Battery is draining in minutes. System feels sluggish, which doesn't sound to be good, right? Now imagine the CPU sleeps peacefully 95% of the time and only wakes up when something actually happens. That is the massive difference between polling and interrupts. This is what we will discuss in this video, that is from 100% CPU load to 5%, why every embedded engineer must master interrupts. In my next few minutes video, I will show you why is polling silently destroying the efficiency of your computer, how do interrupts reduce CPU load, and the real code comparisons that is between polling versus ISR. So let's get started. Please go through the Maven Silicon Confidential Note. So let's understand why polling is destroying your system efficiency. On the left side, you can see we have the polling process. The CPU is stuck in a continuous loop, constantly checking, is the button pressed? Is the button pressed? And 19% of the time, the answer is no. But the CPU is still busy checking again and again. So the result is 99% CPU usage even when the system is doing almost nothing. Instead of the CPU constantly asking, it will tell the hardware, hey, when the event happens, just interrupt me. We have a dedicated hardware for interrupt handling, okay? Now in this situation, what happens, the CPU stays relaxed doing other useful work, or it might go to a sleep mode. Only when the actual event occurs, the ISR run and the CPU handle it quickly and return, right? So CPU usage in this case dramatically drops and you can see it is just 18%. Now if you look at, this is basically the polling version of the code, which is inside an infinite loop, and this is the ISR version. We will discuss more of them in the upcoming slides. Now let's understand what is polling. Polling means your program code sits in an infinite loop and repeatedly asks the hardware, are you ready yet? This shows here an infinite loop, you can see here, and the program is running within this continuous loop. The waiting state which you see is basically the program asking the hardware, are you ready yet? It checks the device again and again. Now here, the chip that you see on the right represents the hardware peripheral such as UART, GPIO, sensor, ADC, etc. The device may not be ready yet, but the CPU still keeps checking repeatedly, and this keeps the CPU busy always, which leads to 100% load on the CPU, right? Now let's check the C code where we have implemented the polling loop. This is a function which you see here, LED operation. This is a simple LED toggle control based on a button press. Now if you see inside the function, there is an infinite loop. Now within this infinite loop, it is waiting for a button to be pressed. Now if the button press is true, it is going to toggle the LED. And again it waits for the button to be released here before accepting the next press. Hence, this process is going to run repeatedly as it is inside an infinite loop. This code finally results in 100% CPU utilization. That's why the polling approach is not a good idea. Rather, there is another better approach where we can use external interrupts. Let's check the same. Now, what is an interrupt? An interrupt is a signal that tells the CPU, hey CPU, stop whatever you're doing right now, something important just happened. A very common interrupt handling is an external interrupt handling. Now let's check what is this external interrupt. Now external interrupt can be an event that could be triggered because of a button press or a sensor trigger, and this basically will be detected via a GPIO pin. The interrupt can also be a UART receiver being ready or a SP transfer is being completed. So these are some of the examples of the sources of external interrupt. Now here I will explain you how a switch button that is connected to a GPIO pin when get pressed generates an interrupt signal. In this section of the hardware, you can see we have a push button switch that is connected to a GPIO pin, and the GPIO pin is configured as interrupt. Now this button is active low, means when the button is pressed, the GPIO pin is connected to the ground, that is the pin goes low. When the button is released or not pressed, the GPIO pin is pulled high, that is the VCC, through the pull-up resistor. Now this button press sets the GPIO pin voltage from high to low, which is called as basically the falling edge. Now the MCU, that is a microcontroller unit, comes with a dedicated hardware called as interrupt controller and a NVIC, that is a nested vector interrupt controller block. Now this dedicated interrupt controller hardware is also called as external interrupt in STM32. Now this is going to detect this falling edge on the GPIO pin first and checks if the interrupt is enabled for that particular pin. Now let's say this pin is, let's say, PA0, right? That is basically the port A0th pin. So this will be detected first by this interrupt controller hardware, and then this controller will send an interrupt request to the NVIC block. Now you might be wondering what is NVIC. It stands for Nested Vectored Interrupt Controller. This hardware is going to receive the interrupt request from the external interrupt controller, and it is going to send the interrupt request number called as the IRQ to the CPU core and signals the CPU core to pause the current execution. Now what the CPU will do now, the CPU will jump to the ISR, that is the interrupt service routine. Now ISR is a part of the interrupt vector table, and that is stored in the flash memory. The ISR gets executed and the desired action, for example in this case toggling LED, will be completed. Once the ISR is completed, the CPU returns to the main program seamlessly. So you can see here in this scenario, there is no constant polling concept at all. If there is an interrupt, then only the CPU reacts to it and take action and come back to the normal operation. Now let's see a C code implementation for interrupt handling. You can see in the main program, the CPU is performing the other operations. For example, it configures the registers for GPIO on interrupts, and it is performing some other operation. Now, if an interrupt has occurred, then what happens? Outside the main, we have declared here the interrupt service routine function. Okay. Now, for example, if there is a push button pressed, then only this interrupt service routine will be called by the CPU, and this particular function will be executed. And after this is executed, it will go back to the main and will continue the operation. So it is not like anymore constantly polling the button status the way we saw in the polling approach. Alright, so finally we can summarize: polling equal to CPU always awake, battery dies fast; interrupts equal to CPU sleeps until needed, low power, instant reaction. The golden rule here is if you're polling a hardware status more than once every few milliseconds, replace it with an interrupt. This single change can turn a 4-hour battery life into 4 days. If this video saved you some debugging time, please hit like, subscribe, and drop a comment. Thank you, and have a happy coding and save that power.